This is the hardware setup of our project. We have three servo motors. We have set our servo motors in such a manner that it touches all the edges on the board. And these are the world coordinates. According to the right hand rule, this is the z-axis, the x-axis and the y-axis. Now we will cover the DH parameters. As shown in the image, our robot is elevated by 4.7 units. We have coordinates 0 and 1 at rotation point 1, hence d equals to 0. We have taken the common normal between joint 1 and joint 2, resulting A1 as 8.16. To calculate d2, we take the distance between the two x-axes between frames 1 and 2, measured along z-axis of coordinate frame 1, and we get d2 as 2.6. To get A2, we measure the distance of the two axes of common normal of frame 2 and 3, and we get A2 as 6.97. The alpha value is 0 since the frame 1 and 2 are parallel, and between frame 2 and 3 it is 90 degrees. Since there is a rotation, D3 is calculated by calculating the distance between x-axis of the frame 2 and frame 3. This is the MATLAB code for our program, and these are the x, y and z values of the base of the robot with respect to the end effector. When we run our program, we get the graphical user interface. These are the DH parameters, the end effector position x, y and z. There are three sliders for three joint angles. As we move the slider, you can observe there's a change in the robot as well as there's a change in the x, y and z position. We have an additional feature of manually entering the theta values. So as I manually enter the value, there's a change in the position of the robot as well as the change in the end effector. An example of our end effector position. The joint 1 is set to minus 90 degrees and joint 2 is set to 90 degrees. When we run the simulation, we get the end effector positions x, y, z. X is 9.4, y is 4.6 and z is 0. When we measure these values manually on the board, we get similar values as in x 9.2, y 4.6, which is pretty accurate.